we discussed some examples of distributions of random variables. There is one more example which we didn't look at. That's because there are too many examples will be boring. So, but this is an important example. So this is what is called multinomial. This is just a generalization of binomial distribution. Binomial means two, multinomial means n of them. So the experiment is following. You have an experiment like throwing a dice or any experiment like anything, something. You drawing something from a box or something, and you have R possibilities are there. Okay, R type of balls are there, and you draw one ball, and there are many balls, and probability of getting one ball is PR or something, but some particular color is PR. Then that's one thing. Or you have a dice with 6 sides, but it can be R sides, suppose. There are R possibilities are there. An experiment has R possibilities. R number of possibilities. R is a number. I'm writing. Okay. R is a number. R is a positive integer. Then you can define this y, and you can repeat this experiment. Okay, repeat the experiment n times independently. Repeat n times. So the omega will be 1, 2 up to R n. Okay, you repeat it n times. Omega will be this. Okay. Then yi be getting the rth one. Yi equal to R. K, where K is between R and 1. If in the ith case you are getting, in the ith result is K, to get the kth type. So you define a new random vector XR. Okay, this is a random vector where Xi equal to, here Xj or something. Okay, Xi is okay. Xi of omega equal to some K. Here K is between. Oh, here it should be n. Sorry. This should be n. This y is yn up to. You have first one random variable y1, y2. This is just the result of the experiment, kth experiment. That is y1 up to yn. But here you have x1 up to x. There n can be anything. But here you have x1 up to xr among these r type. Xi omega equal to k if number of yi omega omega equal to I. Sorry, number of y k omega equal to I. Okay, equal to k. Understand? Number of times the kth type has occurred in this. Let me see whether I have written correct. No, this k is different. That k is between yi equal to this is correct. This is correct. K between r, correct. I is between 1 to n. Sorry. Maybe we should use different notation. 1 second. Let me just root the right notation one by one. You don't even need yi, but that's for that. You have y1 up to yn. Okay, where I use yk of omega is the result of the, equal to yk of omega equal to some I or something. There are too many i's and coming. yi of omega equal to k. If k occurs, kth type occurs in the ith experiment. Okay, but you define x1 up to xr, where here I want to use j. Let's use j of omega equal to some. There I have used k, so I used n, m or something. M is okay. If number of yi omega equal to yi omega equal to j. Okay, this equal to that m. Okay. Is it okay? If you toss a coin, there are two results. You are just counting the number of x, counting the number of tails. Here you are just counting the number of ith one. Okay. Number of jth thing occurs. It's just definition, nothing. You have r types of possibilities in each experiment. You do the experiment n times. Okay, the number of time ith thing occurs. Okay, ith type occurs or jth type occurs or jth type occurs. That is what our xj is. Okay. Now we want to calculate just the distribution, the probability mass function of this xj. That is probability mass function. That is, we want to calculate the probability of the vector x1 up to xr equal to small x1 up to xr, where this is in r power r. Okay, this is what we want to compute. Okay, clearly this is a discrete random variable and all that is clear. These are all, of course, finite, so you don't sigma algebra. There's no problem all that. Okay, this takes only countably many values, and we want to compute this probability. Okay, so for that it's the same thing. I mean, I can directly write the answer. It is just, if you fix a xi, say x1 up to xr equal to some particular pattern, x1 up to xr with n1 n1 x1, with ith1 occurs n1, ith1 ith1 occurs ith or jth1 occurs jth possibility, whatever that possibility is, jth possibility occurs some ni times, nj times. Each jth probability occurs n time with a particular one. You fix one. Okay, fix x1 up to xr. Okay, with jth possibility occurs. I mean, with this is an integer, right? X1 up to xr is an integer. Okay, so I don't even say that x1 up to xr. Okay, x1 equal to xr. So that means the jth possibility occurs with xj times. Okay, this is the fixed one. Okay, then the probability of that
xj occurs nj.
xj, no, xj is the number. Here, this, if this is equal to this, then you fix a particular y1 here. You have a y1 omega up to yn omega, right? In this, in xn omega, you fix some pattern. Okay, some pattern with, coming from, fix some. Okay, let me give another. Suppose you have y1 up to yn, a number which is in that 1 up to rn. Okay, this is okay. Okay, where yi is in this. In this yi equal to r, this is fixed one. Yi equal to r xr times. Okay, that's what it is. Okay, then the probability of this is for a particular thing. Then probability of, you see the probability of y1 up to yn equal to this y1 up to yn. So this is clear. Now this is clear, right? Now this is equal to whatever the probability. So now let's assume the probability also. Probability of yi omega equal to what is it? Yi omega equal to some j is equal to pj. Okay. There are r types. Each one occurs with probability pj times. So then this will be p1 times x1 up to p2 times x2 up to p r times xr. Okay. Here you have fixed a tuple. Among this, there are yi equal to, I mean, this occurs with xr times this occurs, okay? And to, I mean, yi equal to not I, yi equal to some, yi equal to some k with xk times, where k is between r and this. This is just too many numbers are there, but it's a simple thing. You start with an experiment which has r possibilities. Each possible, when I say it, it's very clear. You start with an experiment with r possibilities. Each possibility has PR, the probability is PR. Okay, there are r possibility, each probability is PR. You repeat it n times. Okay, you repeat it n times. So that is this probability, that is this random variable or whatever. This is the result of the experiment from omega. Okay, so then the probability of, so then you fix something. Here, this k occurs xk times. And the probability of getting k xk time is pk times xk, right? Here, each k has pk times xk. So this happens for each one of them. So this is, I mean, this is such that x1 plus x2 up to xr equal to n, right? It is with that. Okay. So this is the probability of this. Okay. So this is for fixing one. For any, only the number matters here. You can fix anything. Probability of this should be, no, this is just I have written. This is what I want to calculate. This is the probability. Our aim is to calculate this. Okay, this is our aim to calculate. So we are proceeding with other reasoning. Okay. Now I write that probability of, you have this random vector x1 up to xr equal to small x1 up to xr. This is a vector in the RR. Okay. That should be equal to first what I have written, p1 power x1, p of p2 power x2 up to pr power xr. Then you have to do the permutation, which doesn't, I mean, which gives the same result. That will be like this, n1 times x1 factorial, x2 factorial up to xr, right? That's all. If you are, even you can directly argue this, or you can, I mean, if you know comparing the result, you can directly argue, or you can first, it is like choosing from n, you want to choose x1 of particular, x2 or xr of particular type. So first you choose the x1. So that will have n factorial times x1 factorial into n minus x1 factorial. But then from n minus x1, you choose the x2. That will be n minus x2 factorial. So that will cancel out, and finally you get this. So you do the calculation, and this will be clear. So this is the result, end result. Okay, this is what is called multinomial distribution. This is a vector. This is a distribution of random vector, okay, which takes values in n, where nr, okay, multinomial. Okay. This is what is called multinomial distribution. I should have introduced on that day, I mean, some 2 days to in the last class. But of course, too many formulas are also not nice. So we will see one by one. Okay, this is multinomial distribution. Okay. We see another example which I wanted to discuss in the last class. So which is, if you have, see, you can have, so let x, y be independent random variables. When you say independent random variables, two random variables are invariant, they should be defined on the same probability space. Then only it makes sense. Okay, independent random variables, but you need not explicitly have the probability space. Okay, because you can always, once you just need the, what is the mass function of this, what's the mass function of this. Once you know that, you can always have a probability space. You need not worry about the what is the probability space? Okay? Because it's always there underlying. When you say independent, you can always define something and get it. And which probability space, it doesn't matter. Only the mass function matters. Okay?
So how do we talk about independence in
It is just the mass function will be the product of the last class we did all that. So the mass function is just the product of them, and you take the probability space as the product space. Okay, you have one random variable defined on omega1 with something, and another on omega2. You take omega1 cross omega2, take the identity function. Where omega1 is all possible values of x1, first random variable. This is all possible values of x2. Since they are discrete, you just take just the countable one, omega1 cross omega2, and the power set of whatever. Just define the identity function that will give the random variable. So you always have, when you say independent, they always have the random variable, and the the probability combined mass density function is just the product. Okay. Suppose if we have two independent random variables, x, y, both geometric, okay, both geometric with following with p. Okay, I mean geometric value as a p, no. I mean the probability of head or tail, which repeatedly until you get a head or something. So then let define z is equal to minimum of x and y. This makes sense. This is real value, so you can take the minimum of them. That is another random variable z of omega, which is minimum of x and y. Geometric with p. Geometric probability has a parameter p, no, the parameter is p. Okay, this is quotation. So z is equal to minimum of xy, and we want to compute this. Okay, so I mean the idea is when you want to compute something, you have to compute this probability of z is equal to some n. Of course, this takes values in. I mean the x and y both takes values in integers. So this should also take integer value. But but z equal to n. This is what you want to compute. But then this may be, so probability of z equal to n is probability of minimum of x and y equal to n. Then you have several union, and there are several possibilities. But instead, if you compute this may be easier. So this is just to show you that it may be easier to compute this. Greater than? Yeah, this is z is greater than or equal to n. This is just probability. Yeah, that is just x. X is greater than or equal to n, and it is just the intersection. Y is greater than or equal to n. Okay, but then since they are independent, since they are independent, this is equal to probability of x greater than n and probability of y greater than n. Okay? And you know what is this? This is just q power n or n minus 1. I am not sure. Doesn't matter, because we will. I mean, it depends on how you started with, which is q is 1 minus p. Okay? Q equal to 1 minus. Okay? Q power n, and this is just again q power n. So q power 2n. Okay. So minimum of, I mean, if this is, from this we can calculate the probability of n, because you know this you know for all n. Okay. Then probability of x equal to n is, you just subtract this from the, I mean, subtract the next one from this. Okay. So that will, so this implies, I mean, you just check, convince yourself by doing this. Check minimum of xy is again a geometric distribution with the parameter, whatever the width parameter. So 1 minus q square, which is 1 minus p square. Okay. This is how you can calculate the mass function of minimum of two distribution. I mean, I didn't give some detail which should be clear to you. Okay. If you compute that probability of x greater than or equal to x equal to 1, you can compute. That will be precisely p power something into 1 minus p power n. And p times 1 minus p power n. If p is the q equal to 1, I mean, whatever the q is. Given q, you take 1 minus q as p, and then that will work. Okay. Now we want to prove the following proposition. This is general, which is what is called convolution product of density function. So if we have x, y independent random variables on the same probability space, which doesn't matter, we need not. Which probability is which does not matter. It is just they are independent random variables with density with mass function fx and fy. Then the sum of the random variable is also, I mean, sum of x plus y is also a random variable. Then x plus y, okay, at it's okay. Shall I use x? X is equal to, maybe use z. Z equal to, see, we define the mass function the whole real line, but it's non-zero only at countably many points. Okay. Fxy z is equal to summation. So the summation is a countable summation, which should make sense. No, then there is no definition. X plus y. What is x plus y? X is a real number, y is a real number, but it's random. You can add those two things. That's also a random variable, right? Okay. X plus y is a random variable. X, y random variable, then x plus y. X of omega plus y of omega. The probability space is somewhere. We don't need it. I mean, we don't even care about it. But still you can add. Okay. So this is just is a random variable, right? Then fx plus y z is equal to x in R, but the sum is over only countably many things. Okay. But when we explicitly know the discrete values, we can directly write. It will only, I mean, wherever it makes sense. Okay. The point is this. Okay. Let me write f of x, fx of x, fy of z minus x. See, when you want to sum over the actual range, I mean, actual points where this random values takes positive values, positive probability, then all points may not occur here. All points of y even may not occur here because z minus x may not make sense for some of them. Suppose if this y takes values, y, the range of y equal to some y1, y2, like this. Okay. Then x is something. Then z minus x, only if it is here, it will take a positive value. That may not even exist for you. I mean, sometimes it may not even exist. Okay? That doesn't matter. But we are just assuming, I mean, except, I mean, these points, it has a positive probability. Everywhere else, it has the probability 0. Then we can sum over the whole real line. Okay? So this makes sense by just, I mean, assuming it's 0 in the all the other places where this doesn't take a positive value. Okay? This makes sense. So this is the proof. Proof is very simple. We want to calculate, this is the density function. So we want to calculate probability of x plus y equal to some z. Okay, that is what, maybe I'll write that. F of x plus y at z is nothing but probability of x plus y equal to z. Okay. Now this is equal to probability, I mean the probability space is underlying probability space. Okay. This is equal to probability of x equal to x takes some value, y takes some other value, so that the sum is z. That's what it means. So that is equal to probability of union of all those x in R, okay, such that x is equal to x and y is equal to z minus x. Okay, right? Okay. When x value takes a value x, okay, y takes a value z minus, then if x is x and, I mean, two x1 and x2 are different, z minus x1 and z minus x2 are different. So for different x, these sets are disjoint. Okay, because it's a function. Okay, I mean, I'm using the fact that x is a function. That when x1 and x2 are different, when the x is different, two different x, these sets are disjoint because x and y are actually a function. It's a well-defined function. Okay, so I'm using that fact. It's a disjoint union. Okay, so since it's a disjoint union, I can write it as a sum. X in R, probability of, again, I'm going to use the independence and y equal to z minus x. Okay, but since independent, this is equal to summation x in R. Okay, probability of, I mean, it's actually a countable union. That's why I'm using sum. Okay, this is the, that's only, it's a countable union. So that's why I'm using sum. Probability of, so this is same as, I mean, this is same as, of course, probability of x equal to x because independent, y probability of y equal to z minus x. So this is like a product of two density function, but this is what is called convolution product.
No, but as you said, it might not even be defined, some of the z minus x.
No, it is defined. It is zero.
Ah,
Okay, that's all. The probability is zero.
right, but it can be zero uncountably.
That's right. Yeah. So
we need to
yeah, it is zero. It is zero. No, that is why when we say sum over summation, when it is non-zero only at countable point, that makes sense. We don't sum over uncountably when we find. It's possible to sum. It's possible to sum. You can define the sum as you take finite sum and then define the net. There is something called net. Using that you can define. Uncountable sum also you define, but we are defining only countable sum. We need not worry about that. Sum is countable. Okay. So this is just a notation x over r, and you are only taking where the is positive. Everywhere else is zero, so it's okay. So this is about independence. So let's calculate something. What shall we calculate? Let's calculate geometric distribution, for example. Okay. X, Y are geometric with P. Okay, this I should use the notation. I said geometric with P or something. This is the notation. Okay. Distribution X and Y are both are geometric with P. This is geometric distribution with that parameter is P. Okay. Then the distribution of xy, fx x plus y at x at maybe n or something. Yeah, at n equal to summation over r p power r 1 minus p power r into p, sorry, there is no p power r, p into 1 minus p power n minus r, right? Up to r equal to 1 to, it's possible up to r equal to 0. We started with 0. I mean, that till now that problem is doesn't matter whether you start with 0 or n. When we define geometric, we started whether we start with, I mean, whether we assume the first one, if the head doesn't occur, whether we assign the value 0 or 1 does not matter till now, because it is just probability. But when you want to compute expectation, which I defined in the last class, there it really matters what you define as. I mean, the expectation will differ based on that. So we should be careful there. When we compute the expectation, we will be more careful. Okay? Now it doesn't matter. I mean, there also that q power n or q, that differs on whether you start with 0 or something, but it doesn't matter. I mean, corresponding to that, you will get something. The answer is same. Okay? I mean, whatever you want to work out, that answer is remains same. The minimum is again a geometric distribution. That statement doesn't change. Okay? But the expectation value will change. It depends on how you start it. So let's be more careful there. So here I am just writing our whatever we have. So this is just, of course, p square summation r equal to 0 to n p square into 1 minus p r, or 1 minus p n. But this is just n times that. Wait. What is n? R equal to n, no? It is n plus 1. N
Summation from r equal to 0 to n minus
0 to n. And it means 0, okay, n minus 1. You want n minus 1? That's what let's be careful when we do the expectation. The point is, no, I think it is n times n. That's what we define. The first one is 0. 0 means there is no head. The second one is n equal to, okay? The n equal to 1, 0th time, nothing occurs. The first one occurs in the 1. So n equal to 1 means in the second one, the head occurs. That is what the probability of 1 minus p power r. Okay? So this will be n plus 1 times p square into 1 minus p power n, right? Yeah, this is n plus 1 toss. The n plus 1 toss, it stops at the n plus 1 time. So first the n is tail, the n plus 1 is head. So that is the probability. Okay. So this is just the in the n plus 1 class, if the experiment stops. Okay. So this is the distribution f of x plus y when you calculate. Which is not geometric or something. It's something else, x plus y. But so if you take x and y, both having geometric distribution, the sum can be anything. That's what this says. But there is an example where, I mean, there is a continuous example. We will come to that, something called Gaussian. There is an example here. The example is Poisson distribution, where the sum, if you take the sum, it will be again Poisson. Okay. Suppose x, I should say it's independent. Okay. They are independent geometry. So suppose xy are independent and follows Poisson. Okay, Poisson is by this I mean, okay, let's say lambda and mu. It can be two different things. There it needs to be same. Xy are independent and x follows Poisson. You know Poisson distribution with parameter lambda. Y follows Poisson with parameter mu. Some other number. Lambda mu are greater than 0. So you have two random variables, they are independent and they follow Poisson, lambda, and mu. So we want to compute. So we know what is fx. Fx at n equal to e power minus lambda, lambda power n by n factor. Fy n equal to e power minus mu power n by n factor. So this is the distribution of that. Then fx plus y at some n m, okay, let's call it n, capital N. Fx plus at n is equal to summation fx at n, fy at n minus n. Okay, and the possibility is it cannot become negative. So the possibility is n equal to 0 to n, right? This number should be positive. So this is the possibility. So this is equal to summation n equal to 0 to n. Let's just calculate e power minus lambda, e power minus mu. I just club it together. And then lambda power n by n factorial, mu power n minus n factorial, sorry, n minus n by n minus n factorial. Okay. Okay. Now I insert n factorial by n factorial. Then you know what you get. You could see. So now this is equal to exactly e power lambda plus mu into summation n equal to 0 to n. Okay. And I have a n factorial in the, I mean, I took a 1 by n factorial out. And this is just, exactly, this is just n factorial, I mean, which is just n lambda power n, mu power n minus n, right? Which is just binomial formula. You know that this is equal to e power minus lambda plus mu into lambda plus mu power n by n factorial. Okay, this implies f of x plus y follows Poisson lambda plus. The sum follows again Poisson, where the parameter gets summed. This is because of the exponential thing e. Okay. And this will happen to Gaussian distribution also. We will see when that is continuous. In that example also, this will happen. I'm telling you beforehand. Okay. This is through direct calculation. The independent variables are usually can be computed using what is called characteristic function or moment generating function. So that will be more easier, and we will see that later. Okay. For example, for binomial, if you do this, it will be messy, but it will be very easy if you use moment generating function or something. We will define it, moment generating function. We will see that. Okay. So that we will see later. Before that, we have already defined expectation. So I will call it expectation. If x is a random variable on something, say on some omega p, then expectation of x is equal to summation x of summation x, maybe x and not. This is a discrete random variable. When I say random variable, till midterm, it is only discrete random variable. After midterm only, you will consider continuous random variable. Okay, so x, then probability of x of omega is equal to x. This is through, see, if this probability space itself is discrete, then this is just summation x of omega, p of omega. Okay, you can write it like that, omega in omega. You can write it like this. If the probability space is finite or countable, I mean, discrete and countable, there is a slightly difference. It can be countable, still may not be discrete. By discrete, I mean probability of omega is not equal to 0. Single point is not 0, right? Okay. It's not, I will give an example later that something is discrete. That is the example you are talking about, I think. It has something to do with that. Okay. We'll discuss. So if the probability of single point may be 0, but still the whole space may be, I mean, probability single point may not be even defined. Okay, but still you can define the probability space on some countable sample space. Okay, so here by discrete I mean the probability of single point is defined, and that is how you take a power. You have the power set here. Okay, that's what I mean. In that case, you can define the expectation of x to be like this, which is same as this. X of just you can sum over the probabilities x of omega, p of omega, where the sum is over omega. But when it is continuous, p of omega may be 0. The probability space may be continuous, but still the random variable may be discrete. So because of that, we use this definition. Okay, so this is the definition we want to use, and I assume you are matured enough to deal with this rather than that. You can, it's enough to deal with that. Okay? Then this is equal to, this is same as like x and r, x of f of x. This is a density function. Okay? Mass function. So you don't need the probability space, you only need the distribution. Sorry, I'm sorry, I forgot to say. Last class I said, but this class I forgot. This is this is definition. It's a random variable. So before this, I mean, I have already said this should come here. Expectation exists. Yeah, I have to say whether it exists. If summation mod x of probability of x is less than infinity. Okay, that is this. You put a mod x here, and that this should exist. Then only expectation exists. So this should come here. I said it in the last class, okay? But today I forgot, directly defined. Then the expectation is defined like this. Okay? Then it depends on, you may be grouping something, something. Then there may be, it may not be well defined. The probability space, you don't have any order. There is no order in this omega, right? Which one you consider first, next one, there is nothing like that. But in the sum, you may be summing over some order and getting something, something convergent. In a different order, it may be something else, right? So it should be unconditionally summable, right? So that's why we use this. This is the right definition to make it well defined. We want to deal with well defined objects, right? That's right. So we need, this is absolutely convergent. Okay, this is only a countable sum. This is absolutely convergent. Then the expectation is defined like this. Okay? So let's see example or properties. Let's see two examples. We can deal with binomial. But there is an easy way of dealing with binomial. So let's do that later once we know the properties, or we can do it now also. And I can go fast. Okay. Example 1. Binomial. Okay. So X is binomial. You have a random variable which is binomial, which follows binomial distribution. Then what is expectation X? This is only finite. You need not worry about the infinity and all. So this is just summation of K n, that is n, okay, that's okay, K into NCK, which is n factorial by K factorial, n minus K factorial, P power K into 1 minus P power n minus K. And the sum is between K equal to 0 to n. Okay, this is the expectation, right? This value X is here, that value X is here, and this is the density function. And I'm summing over everything. Okay, I'm using this formula. X, fx, x. Fx at n is this, okay, and that K is this. So this is the formula. Okay. Now this can be written as summation K equal to 0 to. So I take the n out. I take a n out. So I remove this. 1 second. N minus 1 factorial by K minus 1 factorial into n minus 1. I'm just rewriting in a different way. K minus 1 factorial. Okay. Times. I take a P out. Okay. Here it will, sum will be 1 to n. Yeah, then only it makes sense, no? And here it will be P into K minus 1 into 1 minus P into n minus 1. I mean, this is not needed. I will give you a simple way of doing it. You can write it like this. NP, and this sum will be 1. Because this is just P plus 1 minus P power n minus 1, which is 1. Which is just NP into P plus 1 minus P power n minus 1, which is equal to n. This is the expectation. Huh? Here it is 0 to n. But minus 1 that cannot come here, no? Here it cannot be minus 1, no? Hmm? We didn't remove anything. Okay, 0 factorial is 0 factorial. Okay, it is from 0 to n, but for, yeah. So that's why I'm using this. I mean, I removed the first one will have n, no? When you write the sum, you write it like this. No, we didn't change. You just write each one of them. First one is 0th one is n. We took that n. N minus factorial is also.
We just rewrote things. We didn't change it.
We didn't change, but the value remains the same. I'm just saying the sum is same. We didn't change it. No, here it's up to n minus. Right? K equal to 0 to n minus 1. No, here, this is 0 to n. 1 to n. Yeah, wait. Why is it 0 to n minus 1? It should be, yeah. Finally it will be 0 to n minus 1. The first one, I'm removing the nth one out. Okay, nth one out. So then I'm keeping this as K. This is K minus 1. This I'm just rewriting as n minus 1 minus K minus 1. Okay. So then I'm taking this P also out. Okay. Yeah, I should. Here I have put it. So okay. So I have taken the P also out. But then these things are the same.
Okay, you're multiplying it.
Yeah.
Yeah, you're multiplying.
Whatever the coefficient, I'm just writing in this form. Okay.
The 0 disappears because 0
Yeah.
times
Exactly. Exactly. This is okay.
We can also use the linearity of it.
That's what I'm saying. So I will give you this you check it out. But this is not very important because this is just to compute it directly. But we can use Cesar's linearity and then it will follow immediately. Okay. This expectation is just the sum of, I mean, binomial distribution is just sum of n Bernoulli distribution. So using that, we can find it out immediately. Okay? So we don't need geometric one. Okay, geometric one. Here we should be very careful. So fx at n, x is geometric with p. So x at n is equal to p into 1 minus p over n, right? That's what I want to say. Or you should have n minus 1 if you want, but then you will get a different value. Okay. Now the expectation of x equal to summation n equal to 0 to infinity, okay, n into p into 1 minus p n. Okay, correct, no? So then this is equal to, I take a p out, 1 minus p out. Okay, then summation n equal to 0 to infinity n into 1 minus p power n minus 1. You know this, I mean, where p is between, I mean, p is fixed here, but in general, p is between from here to minus 1. You know, I mean, usually when you want to differentiate a sum, infinite sum, you cannot take the differential sign inside. So suppose if we have some function, summation f of f and x, okay, then d by dx cannot be just taken inside. It should be from 1 to infinity. Yeah. It's from 1 to infinity, correct. Okay. So, yeah, first one is 0. So, this is 1 to infinity. Okay. So, I mean, okay. So, if you have some summation f and x, some infinite sum, when you want to differentiate, you cannot take the derivative inside. You need some condition, some absolutely convergent, something less than something, or some I mean, you should have the absolute thing is less than that for each x, something like that. There should be a uniform bound of that. Okay. But in power series, that happens. This is a power series. If you have summation x power p, okay, x power n, okay, n, where x is defined in somewhere, even if it is complex number. Okay, I mean, I don't know whether you studied in complex number. If you have some cn z power n, some complex, some power series, n equal to 0 to infinity, then you can define it. The derivative is cn n into z power n minus 1, which will be also convergent for each z in that wherever the domain is. Okay, so I'm using that. So if I use that, this is equal to, since this is the power series, okay, so this is equal to 1 minus p into summation. This is just d by dp, right? And this is not p is fixed, but then I mean, if you want, you change p as a variable and then apply at that equal to p. Okay, you don't mind. Okay, so this is equal to this sum, right? N equal to 0 to infinity 1 minus p power n. Maybe there's a minus sign, minus, or I call it q. Okay, I call it q, qn minus 1. That's easy. dq, then there is no minus sign, q power n. Okay. That is what n into qn minus 1. Now you know what is that sum, which is equal to 1 minus p d by dq of 1 by 1 minus q, which is just, I mean, if I write it, will you read? This is equal to 1 minus p into, I mean, the minus will cancel, 1 by 1 minus q square. Okay. But 1 minus q, there is a p somewhere, no? I forgot some p. There is a p outside. So there is a p here. There is a p here. So this will be that p, and 1 minus q is p. Something will cancel, and this will be exactly equal to, oh, this is okay, no? I don't want to write it in a different board. The answer is this. Okay, the answer is q, I mean 1 minus p by p. Okay, this is the answer. Okay, we just compute. This is equal to 1 minus p. There is a p also. Okay. P into q by 1 minus q square, which is equal to p into q into 1 minus q. 1 minus q is p. So this is just 1 minus p by q is 1 minus p. 1 minus p by q. Okay. Anyway, this computation you should be able to do. So that's about geometric distribution. Now let's look at Poisson distribution. So this is third example. So X follows Poisson lambda. I don't think so, because there is not, you can write it as sum of, it will be more, it looks more complicated, no? You can, it depends on the previous one, right? I mean, the xn, the nth value, that depends on the previous one. And how will you write the xnth one? It's not clear. It's not some summation of something. You can try, but this itself is easier. There is nothing complicated. Here also it's easier, but that will be much easier. That's all. So if you use that linearity, it's much easier. Okay, we'll come to that. So x is Poisson lambda, then we want to compute Ex. Okay. Now Ex equal to x is Poisson lambda, so fx at n is equal to e power minus lambda, lambda power n factorial, where n is greater than or equal to 1, n is in, I mean, n equal to 0 to infinity. Okay. So expectation H is n equal to 0 to infinity, n times e power minus lambda. Okay. N times lambda power n into n factorial. Right? Right, no? This is n into lambda power n by n factorial. But then this is just derivative of, I mean, this is just e power minus lambda, d by d lambda of e power lambda, e power, this is just e power lambda. No, lambda times e power lambda. So sorry. Where the n comes? No. No, there is a lambda outside. Sorry. Let's write it clearly. This is from n equal to 0 to 1, no? So I want to get a n minus 1 here, right? So this is equal to e power minus lambda into, so you have to take a lambda out. Okay, summation n equal to 1 to infinity n into lambda power n minus 1 by lambda n factorial. Yeah, that's okay. Which divides, n will go away. Oh, there is no differentiation happening. So sorry, there is no differentiation happening. Sorry, that's all. Yeah. So this is just lambda into e power minus lambda into e power lambda equal to lambda. Okay, that's all. Sorry.
So for this, this is a little counterintuitive because if p equals half, then we are saying that the expected number of throws to get ahead is just 1, but it should be 2, right?
Expected number of getting ahead.
Expected number of throws to get ahead, according to this formula.
Yeah, if you take n minus 1 there, it will be 1 by p. So maybe that will be easier. That will be 2, right?
Okay. So we are saying 1 minus p power n minus.
Yeah, here we are doing it in the earlier one. That one is also okay. That one means it's the second one. It's the same thing. We are just shifting the whole thing. You are saying the expectation is 1, means that it will happen in the second. It's likely to happen in the second one.
Okay. So 0.
So if you, it's just how you define the random variable. I'm starting with 0 or starting with 1. If you're starting with 0, the second one it will happen. That's what it happens. The same thing. It's also saying the same thing. If you start with 1, then the expectation is 2. It will be, the answer will be 1 by p, right? That will be 2. Second one it will happen. Okay? So it's the same thing. We should not get different answer. It is just how you wrote it. So this is okay. This is very easy. Okay. There. Okay, then there is a example where the f of n equal to 1 by n into n plus 1. N is between greater than or equal to 1. N equal to 1. Okay, so first we have to show this takes positive values and I mean countably many values and all that are clear. But we have to see that this is a density function. So first to verify f is a density function, f is a mass function. We have to sum it, summation f of n equal to 1 to infinity. Okay. That is equal to summation n equal to 1 to infinity. 1, this is 1 by n minus 1 by n plus 1. Right? Okay. So let's do a Pn. I mean, I'm not grouping or regrouping. There is nothing happening. This is okay. That is right. But I mean, this is more clear proof. That's all. That's why. Okay? It's telescope is what I'm going to say. But then this is more clear, right? So this is equal to 1 minus 1 by n, right? 1 by n or n plus 1? 1 by n. N. K plus n plus 1, which goes to 1 as n goes to infinity. Okay. There is no grouping or something. This is just clearly this is a sum, whether it is odd or even anything. So this goes to. So this is a density function. Now we want to verify the expectation. Summation n f of n. Right, that is going to diverge. So that is going to 1 by n plus 1. Summation 1 is equal to infinity. So because of that, if you have n equal to 1 to infinity, n equal to infinity, this is equal to infinity. So this is an example where the expectation does not exist. If you have this density function, then the expectation does not exist. Okay. Okay.
Suppose we are doing some experiment and we find probability of something, the expectation for an event is
Not clear. It can, you cannot guess it. It can probably, it's not, I mean, it can be anything. That's what it is. It just means that if you see there can be two maxima, then you say what is the maxima? You cannot say maxima. If you have a function, it has two maxima. You cannot say which is the maximum, right? The maximum value, something like that. I mean, it is something that it's not clear how to define it. You can't expect something. Okay? I mean, expectation is what? It's like you do the. I mean, it is more likely to cluster around there. It may not happen. Okay? That's not exactly that. That's called variance, but. These are all just to get some result, right? I mean, when you do some process, you want to say something. When it doesn't exist, you cannot say in that experiment. That's all. It's not useful. Okay, let's see some properties of expectation. Okay, properties of expectation. So, which is proposition. Okay. So, x is a random variable, y is a random variable, all that. Then the first one is xy, ex, ey exist. Means, or I will define this and then it will be more easier to say that. Okay. Let g phi be a function from R to R. X is a random variable, and expectation exists. Expectation exists. And then E of P of x exists if summation phi of x f of x. Let me tell you what is f of x. x is a random variable with mass function f. So fx. Mass function fx. Okay. P of x, f of x. This is less than b. And this is along expected lines. Expectation of phi of x is nothing but phi of x, fx. Instead of x, you have phi of x. That's all. Okay. And the function is identity, you get x here. This is, I mean, this is like a change of variable formula. You are supposed to have E of phi of x and probability of the phi of x at phi of x, right? You are supposed to have summation phi of x, E of phi of x at phi of x, right? Right? That's what you are supposed to have. Phi of x is another random variable. Yeah, that predefined. If phi is any function, then I mean, previous what? What is the previous definition?
Like sigma mod x.
It's the same thing. No, what is equal? There is no equivalent. This is what is called, you are supposed to have this phi of x such that phi of x equal to phi of x, right? This is what the definition, right? If you want to compute the expectation of phi of x, random variable, you are supposed to have this, where phi of, okay, or you have y, or such that phi of x, okay, expectation of phi of x such that phi of x equal to y. Okay, that's what you are supposed to have. That is equal to that. That's what I'm saying. It is like in an integration, you can say some function and then you can change the variable. Okay? You can assume y equal to phi of x and then you change it. It's like that. So this proof is easy. We want to talk about E of, I mean, the same proof will work for, I use mod first and the same thing will work for phi also. So I will not do it 2 times. So you want to talk about E of phi of x, okay, by definition. This is equal to summation y in R, y, okay, then the probability of or effects of that, right? So which I write it as probability of phi of x equal to y. I have just written the definition. Okay, I have just written the definition. So this is the definition. Okay, maybe mod y. Sorry. I have just written the definition of this expectation. Okay. Now this is equal to summation y in R mod y. Then the probability, this is a set, all those omega such that phi of x equal to omega. Okay, that's what this means. Okay. Now this is equal to x is in phi inverse singleton y. Right? We have already done this. That's what it means. Phi of x equal to y means x is in the set. There may be many x happening this, right? Okay. I mean this x, sorry. Capital X, sorry. Random variable, capital X. Okay. If you want, that set is omega such that phi of x equal to y. Okay, which is equal to omega such that phi x is in x of omega is in this set P inverse of the singleton y. P inverse means the inverse image of that singleton. Many omega can finally get mapped to this. Okay, it is this. Okay. Now this is equal to summation y in R, okay, mod y. Then this is of course equal to probability of x of omega equal to x, where, let me write it, x is in P inverse, here it is small x. This is just the union over all the points in here. Phi inverse y is a set. It is union over all the singleton. That's what I have written. Okay. This is a set. This set is union over all the singleton. X in those singleton is same as singleton of singleton x, I mean. So that's what I have written. So it's the same thing. Okay. But then they are disjoint. Okay. So this is same as you can write the summation here. Summation of x in P inverse singleton y, okay, probability of x equal to x. Okay. Now you can write x is in phi inverse y means phi of x should be equal to y. So this is same as y in R. If you want, you can write it like that. This is phi of x. Okay. Then this is just probability of x equal to y. I mean summation of x in summation of all those. I mean this is just probability of, this is just f of x. I mean probability of x equal to x is f of x. Okay, x is in phi inverse of y. Each y where the sum is over x in that, this is same as summing over whole x, right? You fix a y, sum over all those phi inverse y, all this phi of x, that is same as summing over x over all of r. These two summation will be together summation over x. Here there is no x in the sum, y in the summation, right? You have whole real line. Write it here. You have the whole real line, which is x. Okay. Here you have phi inverse y, phi inverse y, phi inverse y, phi inverse y. Whole of phi inverse y. If you take the inverse image of the range, you should get the whole set. But that is disjoint. That is just partition like this. Eh? Summation. So there is a mod. This is what you are saying. X is in phi inverse y. So here, right. So I should put the summation. You are right. Summation y in R. Okay, now it makes sense. You are right. Good. X is in phi inverse singleton y. Yeah, you are right. Okay. Then phi of x. So that's what I should have done. Phi of x. Then probability of x of x equal to x. Now it's okay. Huh? Here, no, here there is no capital X. Capital X should come inside the set. Here it is indexing. It should be small x. They should be f of x. Now it's clear. Okay. Now this is exactly equal to, this is the right way to write. Let me write it and then pull it down. Summation x in x, sorry, x in R, phi of x, there is a mod here, mod phi of x times f of x. Okay. Now it's clear. Yeah. This is just partitioning this. Partitioning the x. This will be all of x in R, right? All of x in phi inverse y. Or you can interchange it and then that will be easier. Because it's positive sum, you can interchange it. No, it's actually interchanging it, then you get this. Because once you interchange, first sum should be y, second sum should be x. You can interchange the sum, then you get that. This is that we go through all this because we shouldn't make a mistake. Okay? When I make a mistake, so now it's right. You interchange the sum. I'm not writing. Okay, interchange the sum, then you get that. Interchange. You interchange the sum, then you get that. Okay. Okay, so this says basically expectation exists. Once again, I will just write it. Exists if and only if E mod x that exists, that is less than infinity. Okay, that's what this says. What are you asking? Because you want to sum over. I mean, you want to sum.
Of y, therefore y goes to R means 5 of R. That is just R.
Oh, there is no. Yeah.
This is the domain.
No, no, you have a y, sorry, you have a y and then you have phi inverse y. You don't need to do that, right?
That is some of
Yeah, yeah, some more domains, yeah. Each one of them, yeah, correct, correct. You
the
don't need to do
varies
that.
are
No, there is no interchange, yeah, it's correct. Yeah, it is just a partition of this using y. Yeah. Okay. This just says that E mod x, which is defined. I mean, I haven't finished the proof. This is for, so if this exists, this, I mean, from here actually, I don't want to write it, but it's first to say there are two statements here. Phi is a function, then the expectation this exists if and only if this is infinity. Okay. So this is just E of phi of x, right? This is just the mod of that. E of phi. This is just, this is equal to E of phi of x, right? Or whatever the sum by definition. Okay. So that is less than infinity. Then using there is nothing. You just remove the mod and you get the same answer. E of phi of x. That's all. Okay. The same thing. Exactly. Okay. So next is, there are more properties, but I may not be able to prove everything. But that's if we have x, y, two random variable, and we have E mod x. They are both have finite probability, finite expectation. Okay, then E of mod x plus y is also finite and it's linear. E of x plus y equal to Ex plus Ey. Okay. And also E of C times x for some constant, C times x this is just linearity. Okay.
not connected to that. Why should the absolute should exist for the
Phi of x.
Yeah.
That is what this means. No? That is, this is what they come. What is one side? No, no, this is exactly equal to this. This is exactly equal to this. So if this is finite, that should be finite. Without the mod, we need it to prove that that is equal to that. That will, the same proof will work, I am saying. What's your question? The statement is, yeah, yeah. No, no, no. Let's, we don't need the corollary. Corollary is just to, well, where is the corollary? Corollary is to this. Oh, you are saying, oh, you are, no, no. I am saying E mod x and whatever we define, both are same. Except exist means that is some summation, something you wrote. That is precisely E of mod x.
That's okay. I don't get
Now, what is your question?
Yeah.
In this problem or in this corollary, your question is? Okay, what is your question?
E phi of x
Hmm.
can exist even if E mod phi of x don't present it.
Why? How will it exist? E of phi of x exists if and only if E phi of x, this is finite. No, no, this is the definition of exist. Definition of E of phi of x exists. E p x. P x is a random variable. E phi of x exists if and only if this is finite. That's the definition. First statement.
But still that summation can
Which summation? No, that is what we discussed, no, initially. That summation can exist. That the definition of expectation is this E of mod of Ex, x definition Ex exists if and only if E mod x is finite. Huh? That's because this may not be well defined. You may group something and then you get something else, right? There may be some infinity minus infinity happening and you may get a right answer.
Yeah.
In the finite thing, there may be infinity minus infinity happening because you regroup it in some way. Okay, that may not, the Ex may not be well defined. Okay? There are the minus 1 power something you can this get cancelled. No, you can easily get a counter example. I mean, you just need something with some over. I mean, you don't need 1. You can divide it by that summation and you get 1. Okay, so you just need to You have some examples where the sum is convergent, right? By regrouping, this is not convergent, but the sum is convergent. That is the example. Minus 1 power something, minus 1 power n, minus 1 power n divided by n is an example. No? We have to scale it to get a probability distribution. Okay? So those kind of things happen. It's not well defined. Okay? If you sum it over in a different order, you will get a different expectation. That should not happen.
That is independent.
Which is independent. Eh? No, that's a xy2. No independence. Only for product we need independence. Ex time exy equal to e of x, e of y. For that we need independence. This is linear. Expectation is linear for anything.
Yeah.
So the proof, I'll just quickly proof and stop. Okay, you want to talk about, again, it's the same thing. I mean, you remove the mod and do the calculation for the second one. Okay, this is equal to summation x plus y. Okay, f of x plus y at x plus y. Right? Okay. This is okay. Sorry, this is not right. Z at Z. This is okay. This is the definition, right? This is the definition. Expectation of mod x plus y is the expectation of, just writing the definition. Expectation of x plus y is summation over z in R mod z, f of the x plus y as z. Okay. Now this is equal to summation. Maybe I should have written probability. That's easier. Whichever is easier, we will use. Okay. Probability of x equal to z. Now this is easier. Okay. This is equal to z in R mod z. So let's call it x plus z minus x. Okay. Which is same as z, of course. And probability of disjoint union over x in R, wherever it makes sense, and such that the set x equal to x, and I mean, I'm having we can have the intersection y equal to z minus x. Okay. Or you can keep it inside, doesn't matter. You can put a comma and keep it inside. Okay. This is okay. You have a mod.
But we did it.
Assume it to be what? You know independence. I'm not taking it out. You are talking about independence, no? No, we are not taking it inside only. So less than or equal to. Now it's the summation is over. I mean, sorry, z in R, then summation over x. No, there is no summation. It is just this. Okay. Now there is a disjoint union, so you can write it as summation. Z in R. Okay, summation x in R. Okay. Then summation. So this is less than or equal to, I write it as this mod x plus mod z minus x. These are all positive, so you can write it like this. Okay. Then this is just the probability of x equal to x. You just keep it inside, y equal to z minus x. I mean, you can write it as intersection or keep it inside, doesn't matter. Okay. This is okay. This is okay. Now you first take the first system, summation x mod x. Okay. So let's see one by one. This is equal to summation z summation x. Let's see the first one, okay, which is mod x times probability. Then there is a probability of x equal to x, okay, and y is equal to z minus x. Okay. This is okay. Now this is positive. Everything is positive here, so you can interchange the summation. Okay. since it's positive. Now you fix x. Inside there is x, z only here. Z varies over everything means y can be anything. Y assumes all the possibilities, right? If you use the summation. So you have this z. So this just means you take the disjoint union over z in R. Here. Maybe I'll write it in the next one, okay? Summation over here, okay? Which is equal to summation, then plus summation over y. Something, say similar thing here. Same thing will happen, okay? This is summation over mod x times probability of disjoint union of z in R. Okay, x is x, y is z minus x. Disjoint, overall z means y can take any value. That's what it means. That probability is 1. So that is equal to summation x in R times mod x times probability of x in x. Similarly, you will get, if you do the computation for the other one, which is here, you will get summation y in R mod y probability of y equals 1. That's what you will get. If you want, you change it to, where y is equal to z minus x. And z goes through all the value, it will give all the value of y. Of course, the sum union, everything is overcountable one only. So that we are assuming. That's why we are freely using it. Similarly, for the one, the other one is very easy. Maybe I will leave it here. That's more easy, no? Now you replace the mod and do the computation, get that answer. Okay, other one is c times x. Okay, this is very easy. C mod c x times fx of x. Okay, so you can take mod c out and summation mod x times fx. So this will be less than infinity. Okay? I'm not writing all the argument. I am just here in this proof. You have to say that first this is less than infinity, so the expectation exists. Then you do the same computation, removing the mod. You get e of x plus y is equal to x plus y. That is how you should do. Okay? F. Yeah, this implies e of c. Then e of c x equal to c of e of x. You do the same computation. What is f? F of cx. Yeah, f of cx at x, which is same as c is yeah. You have to do the same thing. You have to sum over x in R. It is same like sum over cx in R and So yeah. Essentially is linear. This is not correct exactly. I haven't written the sum. It's like x in R and cx in R, x by c in R, both are same, right? Both the sum is same. So yeah, you are using all that. These things are simple but boring, and but one has to get convinced. Okay. What happened? It turned here. No. Something has happened to that. So it went off. Yeah. The camera is not working. But anyway, it's all easy. So someone can